So hello, everyone. Welcome to the first Interpor webinar of 2025. So my name is Maartje Boon, and it's my great pleasure to introduce Professor Malgo Peczynska. So Professor Peczynska received her PhD in mathematics from the University of Augsburg in Germany and her master in habilitation from Warsaw University of Technology in Poland. She held academic positions at the Polish Academy of Sciences, Warsaw University of Technology, Purdue University, UT Austin, and the National Science Foundation of the USA. And since 2003, she has been at Oregon State University, where she is now a University Distinguished Professor of Mathematics. She has received many awards, including the 2020 AAAS Honorary Fellow and the 2021 SciAm Geosciences Career Prize. Her research is in broadly defined applied and computational mathematics with interdisciplinary applications and collaborations in geosciences, engineering, and material science. So thank you very much, Malgo, for accepting our invitation. And today's webinar will be about Arctic pores. And the talk will last for about 45 to 50 minutes, and it will be followed by questions. And please type your questions in the chat so we can ask the questions at the end of the presentation. So we are very much looking forward to your talk. So please start whenever you are ready.
I'm ready. Thank you very much for the invitation. You can see now the full screen. Yeah, very good. I'm really very happy to speak at this Interpor webinar. I see many names that I recognize as the participants, so thank you for being here, and many names that I haven't recognized yet, people I haven't met. So it's a pleasure, and I hope webinars like that are a great opportunity to start some conversations and maybe collaborations between people interested in working on many of those important topics. I will start by motivation, why I sort of shifted some of my research towards the Arctic problems. Soren, who is here, mentioned his current activity as of the day as recreational activity on the snow. So you see here pictures of me. This is in Oregon, and then lovely picture of South Sister. That's the name of the mountain, and her brother North Sister behind me. I want this to continue. Here's a picture of the ski area I met in the background, and this is the so-called dirty snow, which was one of the things we want to model on snowshoes. Here on the right-hand side, however, is a picture from my recent, let's say, field trip to Alaska, where I went to see the Matanuska Glacier, and you will see some pictures of more pictures on that reflect on the timescales. So the general statement that I think applies to many contexts is relating to climate is that what happens in the Arctic does not stay in the Arctic. You probably have heard the statement in a different context, but what this really means in general is that whatever is happening right now with the climate is affecting, let's say, not just some isolated communities in the Arctic, but in turn, it will affect us all. So simply saying, the climate change that's causing the thawing, we don't say melting, but the thawing of permafrost soils in the Arctic will have impacts on everyone elsewhere. In particular, here is a list of my collaborators, and on the right-hand side, you see a picture of me and former postdoc Zach Hilliard. We are actually visiting Florida at a workshop, and we went to a park there, and you see an alligator behind us. So you see here the gray alligator. And so I guess the reason why I'm mentioning this picture is, when I have this picture is is because the alligators will be affected as well by what's happening in the Arctic. So that's a quick way to wrap this whole idea. So again, this is a picture that shows a lot of my collaborators over the years, and those listed in red have been the most recent collaborators to this whole project. And I listed also some of the current students who are here on the call. So thank you very much for doing all of this and for working hard and motivating me every time, every day. Thank you. So what is the talk about? The talk is about, this is interpore, so it's about pores, and specifically about the pores and porous media in the Arctic. So in the middle, you see a picture of permafrost soil in Herschel Island. So if you look this up, it's actually not really easy to visit Herschel Island. It's an isolated island off the north coast of Alaska. And I want to visit it, but it's very inaccessible. So what you see here is essentially a permanently frozen portion of the soil called permafrost. Above it, you see the so-called active layer that we focus most of our efforts on. And our previous work has been on modeling the active layer with assuming some boundary conditions on the ground surface and assuming some boundary conditions from the permafrost layer. We have shifted now to work also on the snow that covers the permafrost occasionally. And of course, one should also then include the atmospheric boundary conditions in the air. So there are lots of processes that you would want to model. Today we'll focus mostly on the freeze and thaw processes. We will also focus on the fact that permafrost is a porous medium. So we will use pore to Darcy upscaling. We will also draw analogies of modeling from modeling the soil as a porous medium to modeling the snow. You will see it's not all that impossible. In fact, when you think about this, it's actually quite possible. And then we will talk about the coupled permafrost, so soil and snow models. All right. We are, of course, not the only ones who have looked at this whole big picture. There has been tremendous amount of geophysics literature and geotechnical literature focused on modeling permafrost and processes in the soils, as well as there's some work on coupling snow and the soils. But I do want to mention that we look at that problem differently. We look at the computational schemes, we look at modeling from first principles and trying to combine and unify things while we are trying to match what we are doing with what practitioners do. So I hope that you will find that our approach is valuable in the sense of trying to get things from first principles. All right, so there we go. At the pore scale, the permafrost looks like that. I have here a picture from a paper by Kalmels. You will see later references to it. It's a very interesting paper with a lot of tomography results of the permafrost soil. On the right, you see a picture from a paper that I will also cite by Kempfner and et al., which shows the structure of the snow. So now, soil is made of rock and water primarily, and of maybe some pockets of air. And that water can be both in the ice, so solid, and liquid phase. So you see here a cartoon at the bottom of the partitioning between the phases and components. The components are here. Water is the only component in the soil that can be partitioned between ice and liquid. At the temperatures we are interested in, there's likely no vapor. So we are only looking here at the solid and liquid phases. At other temperatures, there may be some vapor in the soil. Snow, however, might have some dust particles in it, but it's primarily made of ice and